All right, well, welcome back to Stately Pitcher Manor. And in this lecture, I'm going to talk about the vapor pressure of solutions. And let's just imagine, if you will, a couple of beakers. We'll put these on like some kind of surface here. And so here's a beaker, and then here's a beaker. And let's actually make this a little more beakerish. There we go. Beakerish. And one beaker will just put pure water. And then in the other beaker, we'll have some kind of sulfuric acid solution here. So I'm going to draw just, oops, that's the wrong color. I want to make those red, sorry. Doesn't really matter, I got these colored pens, so I got to use them. So we've got our solute, our sulfuric acid particles there. Well, they're going to dissociate because it's a strong acid, but we'll worry about that later. Let's go ahead and then put this under a glass dome here. So we'll seal it off from the rest of the surroundings. So this is our system. So what happens over time? Well, over time, what we see happening is the level of the water goes down until there's none left. And the level of liquid in the solution container goes up. And so this is now dilute, so DIL, dilute sulfuric acid. There's fewer, or there's more volume for the given amount of particles. Now, why does this happen? Well, let's think about it for a minute. So let's take a look at just a small volume of the pure water, and there's going to be a vapor pressure associated with the pure water. Now let's take a similar volume, or not a similar, the same volume of a solution, sulfuric acid or sodium chloride, whatever. In that volume, there's actually fewer water molecules. Why? Well, some of the space is occupied by the sodium and chloride ions for sodium chloride, or by the protons and sulfate ions with sulfuric acid. So those take up space. So there's fewer water molecules. With fewer water molecules, there's going to be a lower vapor pressure, because your pressure should be, proportional to the number of amount of stuff you have. So what this experiment shows is that vapor pressure, call it P vape here, vapor pressure of a pure substance is greater than the vapor pressure of the solution for non-volatile solutes. Okay, so what can we do with this? Well, it's not just the case that the vapor pressure of the pure liquid is greater than the vapor pressure of the solution, but we can actually quantify this. And the way that that's done is with something called Raoults Law. And Raoults Law states that the pressure of a solution so I'll just abbreviate that as SOLN, equals chi of the solvent times the vapor pressure of the pure solvent. So let me just write those out here. So this is vapor pressure of solution. Chi is, if you remember from the first lecture video for this chapter, chi is the mole fraction. And then, of course, P naught here, let's put the little zero, we say P naught, N-A-U-G-H-T, or N-O-U-G-H-T? Anyway, P naught of solvent is the vapor pressure of the pure solvent. So we could go ahead and use then this equation in some calculations, and we'll do that in the workshop when I talk about vapor pressure. So, you know, if you had a measured vapor pressure of a solution and you knew the vapor pressure of the pure solvent, you could calculate the mole fraction of the solvent. In fact, you can actually do that, use this to do calculations to get molar masses. And I'm not going to do that in this video, we'll do that in a workshop. So yeah, it's kind of a cool thing. Now, this is for non-volatile solutes, but actually it doesn't have to be. Okay, Raoults Law is actually general, so it doesn't matter whether your solute is volatile or not. The solute can contribute to vapor pressure fine. I mean, when we looked at when we were looking at let's see here. Just the sort of general case that we started with, we were looking at non-volatile solutes, but we can apply this a little bit more, and let's go ahead and look at another version. So this is for non-volatile solutes, and let's look at another version for mixtures of volatile liquids. Now what does volatile mean? Well, volatile just means that under regular, typical pressures and temperatures, there is an appreciable, a significant vapor pressure. It means that it evaporates pretty readily. So if you think about it, water will evaporate. That's volatile. Something like, solids can be considered volatile. Like some will just, disappear away. Dry ice, for example, solid carbon dioxide sublimes. It has a vapor pressure. But, a chunk of aluminum doesn't have any vapor pressure associated with it at normal, regular temperatures. So it's non-volatile. Basically, volatile is anything that if you heat it up a little bit, it's going to turn into a gas, okay? Within reason. Obviously we could, really crank up the heat on most elements, 1,000 degrees Kelvin, and they're going to vaporize. But so what we can say here for Raoults Law for mixtures of volatile liquids is that our total pressure is going to be equal to the pressure of each component So, we've got component A and liquid A, liquid B, maybe liquid C, D, E, etc. And the pressures for each component, the partial pressures for each component, of course, are equal to the mole fractions of that component times the vapor pressure of that pure component. So plus chi b p naught b plus dot dot dot. So you can do this for as many components as you want. Usually they're used for binary mixtures, for mixtures of just two components. So we could actually plot this if we wanted to. And let's see. Yeah, maybe let me just rewrite this real quick so that I can squeeze in my figure here. So that equals chi a p naught a plus chi b p naught b plus whatever other terms we have. Now we could plot this, and let me get my axes here. So let's go ahead and plot our vapor pressure. And we'll plot it versus chi a there. And we're going to go from 0 to 1. And actually over here, I'm going to have another y-axis here, just because it makes things a little bit easier. So let's do this. For an ideal solution of two volatile liquids, A and B. So this is our system here. So when we have no A, our mole fraction, so what we would do is we make up different mixtures with different mole fractions, different ratios, and measure the pressures. So when we have no mole fraction of A, that means we have all B. And so we would have, that would be equal to P naught B. Now, if we had only A, our mole fraction of A was 1, then we'd have P naught A. And it's not necessarily that A is lower, the vapor pressure is lower than B, just that's the way I drew it. And so you could look at these independently. And so I could say that, my pressure due to A is going to increase in a linear fashion because it's just pressure of pure A times mole fraction of A. And then the same thing with my pressure of B. And of course, adding those two together gives us our overall pressure. So this top line here is the overall total pressure. And it's just the pressure due to A plus the pressure due to B. So if I had a mole fraction of like 0.75, I was right there. I would say I have that much pressure due to B and that much pressure due to A, the vapor of A, the vapor of B. And those add up together to give us this total pressure there. Now this is for what I've called an ideal solution. And what is an ideal solution? An ideal solution is one that follows Raoults Law. So not all solutions follow Raoults Law. Let's take a look at some of those. And let's think about what types of non-ideal solution and Raoults Law. let's think about what types of deviations from Raoults law we might see. All right, so I'm going to draw here. I've got a couple of examples here. And so in the first one here, let's do ethanol and hexane. So let's do ethanol / hexane. And then, so that's 0, that's 1. And we will have chi here, mole fraction of ethanol. And so we would see that, we'd have our expected curve would look something like this, like we saw last time. So P naught ethanol, and here's P naught hexane. But in reality, what we see is the following. We see that the vapor pressure is actually greater than what we would expect. Okay, we can actually see that from these curves as well. So the red ones are what we actually see. Okay, so here's our actual behavior. And actually it shouldn't, the actual behavior, it shouldn't curve up quite like that. It should be more kind of like that. But you can go ahead and look at probably a more accurate representation in figure 11.14. Now, we call this a positive deviation. Positive deviation from Raoults law. And it happens when we have very weak solute-solvent interactions. So I'll say weak solute-solvent interactions. So that means that the attraction between ethanol molecules is greater than the attraction between ethanol and hexane molecules. Also, the attraction between hexane molecules is greater than the attraction between ethanol and hexane. So the attraction between molecules of the same type is greater than the attraction between the molecules of the different types. Now, we can do the same thing for other systems that show the opposite deviation, the negative deviation, like water and acetone. And so we'll have P naught acetone, and then here we've got P naught water, and we'd expect things to be like this. And in actuality, what we get is we get a lower pressure than expected. And so we get this lower pressure. And that's a negative deviation. A negative deviation from Raoults law. And here we have strong solute-solvent interaction. So what that's saying is that the interactions between water and acetone are actually stronger than the interactions just between acetone molecules themselves, or even between water molecules themselves. we get the ideal situations in things like, let's say a mixture of benzene and hexane, or benzene and toluene, which are very similar. So if all of the interactions are about the same, then you'll have an ideal solution. If they aren't, then you'll have positive or negative deviations. Now, if we drew the structures, we'd see that ethanol is polar and hexane is nonpolar. So that explains why there are weak interactions between those guys. So that's going to be a positive deviation. Water is polar, we know that, and acetone is also polar. So we could see how there might be a negative deviation. In fact, water likes to hydrogen bond. Acetone can't hydrogen bond to itself, but it can accept hydrogen bonds from water. So the water-acetone interaction is going to be stronger than just the acetone-acetone interaction. And that explains then the negative deviation. So, you know, you can kind of think of, I think sometimes the negative deviation is a little easier to think of because you can think of, oh yeah, the two different components are holding on to each other pretty tight, so the vapor pressures will be lower. Yeah, this is the sort of real world version of Raoults Law when it's applied to non-ideal solutions. So what I want you to understand is, you know, how these cases arise, positive deviation and negative deviation. And then in the workshop on vapor pressure, we'll look at using Raoults Law for actually doing calculations involving molar masses. Alrighty, so that wraps up this lecture. And until next time, I'll see you at the Gray House with the white trim.